Hi, I'm Jennifer Comstock, and I am presenting a summary of ARM observations for land-atmosphere interactions and boundary layer process studies. The ARM user facility deploys comprehensive atmospheric measurements at observatories around the world in support of process studies of clouds, aerosols, precipitation, and radiation. ARM is closely aligned with the DOE Atmospheric Systems Research Program, which funds science using ARM observations. ARM also supports model development activities and is closely aligned with E3SM, the DOE Earth System model, providing diagnostics and metrics datasets compiled for model evaluation. ARM supports these research activities through its operation of 6 ground-based observatories in diverse climate regimes to support critical community needs and model development activities. ARM has expanded its capabilities to include land-atmosphere interactions and boundary layer process measurements over the last decade to support routine large eddy simulations over ARM sites and expanded its analysis tools and science products to support these activities. Aerial platforms are also expanding to further augment ground measurements and provide spatial context. I will touch on each of these activities throughout the remainder of the presentation. ARM currently has 3 fixed observatories and 3 mobile observatories deployed pole to pole on ships, often with concurrent aircraft campaigns. ARM observations started in 1992 with our longest running sites in the U.S. Southern Great Plains in northern Oklahoma and North Slope of Alaska in Ukqiagvik, and has an additional fixed site in the eastern North Atlantic on Graciosa Island. ARM's 3 mobile facilities have been deployed around the world, denoted by the gray circles, including a longer over 6-year deployment in Aliktok Point, Alaska, to support extended Arctic studies. Each observatory includes a comprehensive set of measurements, which includes background atmospheric state, a variety of surface energy balance, surface fluxes, and surface properties such as soil moisture, and temperature. ARM also provides profiles of aerosol, cloud, precipitation, and thermodynamic profiles using its LiDAR and radar remote sensing capabilities. We also have a wide variety of aerosol measurements that measure near-surface in situ aerosol properties and aerial measurements on several different platforms, including crewed aircraft, UAS, and tethered balloon systems. Information regarding these capabilities, observatories, field campaigns, and data products can be found on arm.gov, our website, and all data is freely available through a customized data discovery tool. As part of the 2014 Decadal Vision, ARM implemented routine modeling capabilities with an initial focus on shallow cumulus clouds at Southern Great Plains site. The primary objective of Lasso is to provide a link between ARM observations and global scale models to improve process understanding and also improve observational retrievals. To support this activity, ARM has expanded its spatial measurements to create multiple large-scale forcing and model evaluation datasets, which are distributed through our model observation data bundles. There are currently over 1,000 simulations for 95 shallow cumulus cases between 2015 and 2019. The Southern Great Plains site was established in the early 90s with the original design of having a network of extended facilities around a heavily instrumented central facility, approximately the size of a GCM grid box at the time. The primary science objectives at the Southern Great Plains sites currently includes aerosol processes, boundary layer processes and land-atmosphere interactions, aerosol cloud interactions, and shallow and deep convective cloud life cycles. In 2016, ARM expanded its measurements at 4 of the extended facilities denoted by the red dots in the map, located approximately 40 to 50 kilometers from the central facility, which is the orange box in the middle. These sites include more extensive surface measurements and profiling capabilities. Each of these sites includes a wide variety of surface properties, fluxes, and radiation, such as atmospheric state, eddy correlation fluxes and turbulence, latent sensible heat fluxes, soil temperature and moisture, surface energy balance, and broadband radiometry. Also located around the central facility, around 15 kilometers from the central facility, are a network of radio wind profilers, which are denoted in blue on the map, and a network of X-band radars and a C-band radar, denoted in green, to support the deep convective science objectives. These locations were chosen to represent the inhomogeneity of surface properties from the Arkansas River to the east, which is a hillier terrain, to croplands and pasture across this east-west gradient across the southern Great Plains domain. In addition to these surface measurements, ARM has deployed several profiling instruments, including the Doppler LiDAR, which provides horizontal winds and vertical wind statistics, spectral infrared interferometer measurements, and 3-channel microwave radiometer measurements. The area and microwave measurements can be combined to derive vertical profiles of temperature and humidity and cloud properties such as effective radius and liquid water path using the optimal estimation retrieval developed by David Turner. This algorithm is now being run operationally at the Southern Great Plains Central and extended facilities, as well as select mobile facility deployments. These profiling measurements, coupled with the surface measurements, can be used to derive water vapor fluxes, boundary layer turbulence structures, and land surface atmosphere feedbacks across this SGP domain. At ARM's main observatories, there are additional profiling capabilities deployed, including radiosondes, micropulse lidars, and ceilometers. These measurements are used to derive the planetary boundary layer height, or PBL height, which is a key parameter for boundary layer studies and can be directly influenced by the topography, surface properties, and radiative forcing. Our ARM science translator, Damao Zhang, has implemented the PBL height retrievals using each of these measurements to produce and is working to produce a best estimate PBL height value-added product. He is evaluating the pros and cons of each method and comparing with the more reliable but reduced temporal resolutions of the sonde measurements. Some of the results of the comparisons for a well-mixed boundary layer case is shown in the figure on the right. This product should be available later this year. Also deployed at ARM's main observatories is the Aerosol Observing System, which includes a broad range of in situ aerosol instruments. The primary measurements include aerosol absorption and scattering, aerosol concentration, including black carbon concentration, and particle size distribution measurements, CCN and hygroscopic growth measurements, as well as composition and ice nuclei. Also included in the AOS are trace gas measurements and additional gas concentration measurements. The complement of these gas instruments varies across the AOS systems. Aerosol translator John Schilling has been developing several new data products, including merged aerosol size distribution, hygroscopicity parameter, and improved composition and chemical speciation properties. One of ARM's AOS mentors, Yannick Yoon, has published a journal article that describes the various components of the AOS system and further details regarding the instruments and mentors for each instrument can be found at the website listed at the top of the page. Although carbon and greenhouse gas measurements are not part of ARM's core mission, ARM does support a variety of measurements at several locations. This includes the Ameriflex measurement component, which is deployed to the North Slope of Alaska and the Licktock Point sites, as well as greenhouse gas measurements at a Licktock and our Eastern North Atlantic site. This instrument is now retired. We also have a CO2 flux system deployed to our Southern Great Plains Central Facility that, in addition to CO2 and H2O fluxes, it has the full complement of surface measurements that I've been describing. Concurrently with these measurements are those on the 60-meter tower at SGP, which includes additional CO2 and methane concentration measurements and isotope ratios. These measurements are made at 2, 4, 25, and 60 meters above the surface. In addition, ARM has performed routine carbon measurements at SGP, deploying many of these instruments on a Cessna aircraft, which was flown between 2008 and 2011, and additional carbon-focused measurements over the North Slope of Alaska in 2015 using the G1 aircraft. All of these measurements are available on the arm.gov site. ARM has also deployed a tethered balloon at a Licktock Point since 2016 and SGP since 2019, typically in campaigns lasting several weeks at a time. The TBS operates up to 7,000 feet or just over 2,000 meters. The TBS instrument suite includes a number of miniaturized instruments that mirror and augment measurements at the surface. This includes atmospheric state variables, cloud properties, aerosol properties, gas phase, and a thermal camera. Jesse Cremian, a member of our Licktock science team and ARM mentor, has recently published a paper examining the vertical structure of aerosols over the Licktock Point site using the TBS measurements over a 3-year period. The figure at the bottom demonstrates the ability of TBS to move in and out of cloud, where cloud is denoted in gray, which is a cloud mass derived from the Ka band radar or KASER instrument, which is deployed to all of our fixed observatories, as well as mobile facilities. It also shows the vertical variation of aerosol as it porpoises up and down through the atmosphere. A new capability that ARM is developing is its mid-size UAS. The instrument payload is being tested in partnership with Mississippi State University, and there are several similar measurements as deployed with the TBS, but with additional payload capacity has expanded cloud and aerosol property measurements and filter sampler capabilities. ARM has also been testing a new high-resolution multispectral camera that is producing high-resolution images of spatial distributions of elevation of the land and canopy, as well as various measurements of vegetation index and water index. And these are shown in the figures. On the left is the elevation, and you can really see the difference between the cropland and the top of the forest elevations. And then simultaneously the vegetation index on the right. So I've provided you with a brief overview of a broad range of ARM capabilities. By combining these sets of capabilities, we can build synergies across measurement systems to apply to focused science objectives. One example is to anchor field campaigns at fixed and mobile observatories and augment these with aerial capabilities or guest instruments. For example, the high-scale campaign aimed to study shallow cumulus clouds and their coupling with the surface and boundary layer. They had the Gulfstream 1 aircraft, which flew over the main central facility and boundary layer profiling sites, designed to quantify the influence of land, boundary layer, and aerosol properties on shallow cloud life cycle, with the goal to improve model parameterizations of land-atmosphere interactions and evaluate LES and cloud resolving model simulations of boundary layer processes, cloud microphysics, and aerosol properties. Shown on the right is observations from a 2013 new particle formation study, which deployed a TBS over the Southern Great Plains site to understand the representativeness of aerosol measurements at the surface and discover that highly hygroscopic nanoparticles were initiated at the top of the boundary layer, as demonstrated by the increase in nanoparticles as the tethered balloon rose through the boundary layer and mixed down toward the surface. Lastly, I wanted to leave you with some ideas about ARM's future directions and opportunities for collaboration. ARM will begin packing up this month its third mobile facility currently deployed at a Licktock Point to relocate to the Southeast U.S. This will be a long-term deployment up to 5 years with science objectives focused on aerosol processes, convective clouds, and land-atmosphere interactions. We are planning to include several supplementary sites around the main site, similar to the Southern Great Plains boundary layer profiling sites. We are currently focusing on determining the location of the main and supplementary sites, working with the site science team led by Chongai Kwang to develop the instrument suite. Chongai will be providing an overview of the science objectives for this campaign during the next presentation. With the Licktock Point site closing, ARM will be examining the science objectives of the North Slope, Alaska site and determining the best instrument suite to support the research that is most crucial for this rapidly changing environment. There are several potential partners in this region, such as NOAA, who ARM has partnered with on several aerosol measurements, as well as NG and NEON, which could be a good source of collaboration on both land-atmosphere interactions and ecosystem studies. In addition to the TBS and UAS capabilities, ARM's G-1 aircraft was decommissioned in 2019 and will be replaced by the Challenger aircraft, which is undergoing modifications to accommodate instrument racks and wing pods. This platform will have increased payload capacity and flight duration, opening up opportunities for continuing to enhance capabilities for aerosol cloud and land-atmosphere interactions. That concludes this presentation, but I wanted to thank the organizers of this meeting for the opportunity to present to you today. Thank you.